I don't remember on Friday, did we get to electron spin?
I think we did.
So there are 4 quantum numbers. This is the last of the 4. Quantum spin can have either positive 1/2 spin or negative 1/2 spin. The whole idea of electron spin is important because the fact that electrons need to have pairs of them in orbitals. An orbital is a very small confined space where 2 electrons can be. If they're going to be in this small space together, they would, you think, tend to repel one another. So that's why it's very useful because they are spinning. They're in a constant vibrational or rotational motion. When you have one charged particle going that way, and then the same charged particle, well, the same type of charged particle going that way, they have opposite spins, and therefore they can kind of attract one another. They don't really attract one another, but they can be together and deal with each other. So possible values for spin are positive 1/2 spin and negative 1/2 spin. They can't be any other value. Now, the next slide has several sets of 4 quantum numbers. Some of these are legitimate sets of quantum numbers, but others have something wrong with them. Is the first line here, 3, 3, 0, negative 1/2, is that a legitimate set of 4 quantum numbers?
No.
It's not.
No. It's going to be negative.
It's not
Well,
possible.
Amherst?
Because L is n minus 1, so you can't have 3.
So if n equals 3, L can only be 2?
It can be like negative 2.
Oh, you were doing so well. L goes from 0 up to n minus 1. Doesn't ever go negative.
Oh, that's M sub.
Yeah. So, yeah, this thing right here makes that a bad set of 4 quantum numbers. If you have an n equals 3 in the 3rd energy level, the L values go from 0 up to n minus 1. So it could be, this number could be 0, 1, or 2, not 3. Okay? These other quantum numbers are okay, but that one right there is no good. So that's a bogus set of quantum numbers. There's no electron that has those. Right? What about the second line? Is it okay?
No. Yes.
Yeah, this is ML. That's an L, and it's fine. I'm not trying to be a jerk for correcting you, because I know that L looks like a 1. What's the matter with that, or is it okay? It's okay. Others say that it's okay. Here's what the deal is. N is all positive integers. L goes up to n minus 1, so that's an okay L value. M sub L goes from negative L up to positive L. So within an energy sublevel, which is what the L is, the M sub L values go from negative that number up to positive that number. So that could be anywhere from negative 3 up to positive 3. That's in that range, so it's fine. And then the negative 1/2 spin, it would be that's legitimate M sub S.
So would it be TM?
Now, for an L value of 3, remember the L values have special names. If L is 0, we call it S. L equals 1 is called P, L equals 2 is called D, and L equals 3 is called F. So we're talking about the 4F region of the periodic table for this electron. We're not going to go that far as to identify what L is.
That's like LA.
Yes. Okay, that was the second line. So anyway, second line is good. Third line?
Good.
It's fine. All these numbers are in the appropriate value ranges. This is a positive integer. That's all it has to be. That goes from 0 up to n minus 1. That's in range. This number goes from negative L to positive L. So given an L value of 1, this would be 4p. That goes from negative 1 to positive 1, and that's in that range. And so that's got to be positive 1/2 or negative 1/2. So line number 3 is good.
Wait, can you? I'm forgetting like what the requirements are
For which one?
for each one.
These have to be positive integers. and you already wrote that down. These have to go up to, they go from 0 up to n minus 1. So within an energy level, the size of the energy level dictates how many L values you can have. The bigger the n, the more L's you can have. So that goes from 0 up to n minus 1. These numbers depend on the L value. These go from negative L to positive L. So like if L equals 3, that goes from negative 3 to positive 3. If L equals 1, it's negative 1 to positive 1. Okay, so you're running through that range. Including 0. Yep, Johnny?
For the second M, what's the sub?
This is M sub L, that's M sub S. Spin.
So
Yep.
M sub S either always has to be negative or positive half.
Yes. So when we look at the fourth line, 2 and 1, that's okay. 1 and negative 1, that's okay. What about that negative 1? Not okay. That fourth line is bad for that one right there. Yeah.
Can L or M sub L be decimal?
Never.
fraction?
Nope, they're all integer numbers. Last line?
No.
What's the matter with it?
I'll go.
Okay.
Yeah, this term, it goes from 0 up to n minus 1. It's never negative. Okay? All right, good. So that just gives a little review for the quantum numbers and the possible values for the quantum numbers. And let's move on. Which of these orbital designations are incorrect? Now, I'm going to remind you that when you have a term like this with a number and a letter, the number represents the n value, and the letter represents the L value. When L is 0, that's called S. L is 1, called P. When L is 2, it's called D. And when L is 3, that's called F. Yeah?
Yeah.
1s, is that possible?
Yes.
Yeah. 1s is the first energy level or some level. So, I like that one. How about 1p?
No.
No, 1p doesn't work because the n value is 1 and the L value is 1. That L value is too high for the n. So the first energy level has 1s and that's it.
So after, it just goes.
Yeah, after, like, you can have an L equals 4, that would be a G.
Yeah, so it just
And L
goes
equals
down.
5 would be H.
Right?
Yeah, after F. Yeah. So, 1p, we don't like. How about 7d? Does 7d exist?
Yes.
It's possible. Are there any elements that have a designation of 7d on the periodic table?
No.
No, there's not. We need an 8th row.
What about RF, DB, SG, DH?
They're in the 7th row. In the 7th row, there's 6d. If we want a 7d, we need to go another row.
Oh, got it.
Is there a periodic table?
Not yet. I don't think there's any elements higher than 118 that have been produced. Yeah. Okay, so 7d is legitimate, even though there are no elements that are that size yet. There may be down the road. Maybe one of you will discover it.
Maybe you wrote me.
Elizabethium. That's what we'll call it.
That one has a nice resolution. It
Yeah.
sounds really
Oh yeah, but
Yeah.
no one named the
Rahium.
good.
Nice. Emruthium.
That actually
So always have to be a
What's that?
So always have to end with a ium.
No, they have lately though. All the
Einstein.
yeah, all these are eums. Yeah, all these lately have been eums. All the way back to, gosh, back all the way to 89. Radon was the last one that didn't have an IUM at the end. Yeah.
no one ever named elements like after themselves.
Not after themselves, no. No.
I have to
Because chemists or physicists don't have the authority to name elements. That job goes to this group called the International Union
actually
of
a
Pure and
thing
Applied
for that?
Chemistry.
It's a group.
I have to be now.
To name you
They do other
elements.
things. They establish what standard measurements are. Like they're the ones that
Like
define
1
what a
ATM.
meter is and what a gram is and that kind of thing. Yeah.
That's so cool. But then it's also
They're like the original.
Yep. They have so much power.
They do! Over all of our lives.
Okay. So anyway, how about 9s? Is 9s a possible energy
Yes.
sublevel?
Yeah.
That's fine. Once again, we don't have a 9th row on the periodic table to have 9s, but maybe someday. And so, I like that one. What about 3f?
No.
Now 3F is not possible. Because if n equals 3, L can't equal 3 as well, and that's what F means. L equals 3. So that one's a bad one. 4F? What about 4F? Yeah, 4F is possible. And the lanthanum row there, that starts with 4F. What about 2D?
No.
Again, it's the no. You can't have n equals 2 and L equals 2. So, no good on that.
Okay, so the number before the letter is always
That's the n value, the energy level. Yep. And the letter is the sum level.
On the periodic table, where is the S? I remember learning this.
Yep.
this year, but I don't-
Johnny, can we have the camera over here? Look at this guy.
Okay.
Sorry to interrupt you, Johnny.
I know you're used to it from Peter.
Peter.
With Peter?
Peter. Who?
Periodic table. He needs to see the periodic table.
S's are in here, Nina. P's are over here, with one exception. Who's over here that's not a P?
Helium.
Yeah, helium. It's kind of tucked away up there in the fold.
That's an S, right?
Yeah, it's one S is hydrogen and helium, and then we start with no exceptions. So S's are over there, P's are over here, D's are in here. Now I want you to remember about the D's, and I will go through and show you why this is later on too. S's and P's are always the same energy level as whatever row number they're in. So in the first row is 1S. The second row is 2S and 2P. Third row is 3S, 3P. Fourth row is 4S here and 4P. So the rows are always going to indicate the energy level. The D's, however, D's wind up being a high energy sublevel. They actually overlap into the next row. So in the fourth row is 4S and then 3D. Remember how the D's are kind of overlapping like that?
Wait, so
Because a D is a high energy sublevel, it's actually higher than the next energy level's S. So you got 3S, 3P, and 3D, but 3D comes after 4S.
Wait, did you say that all the P's on that side, is that past the black line, or is that?
No, from right here.
Okay.
Yep. This separates G's are there and P's are there.
where are the F's?
F's are down here, these two rows. Those two. Got this?
We like know the periodic.
But if you just remember what I just said, the periodic table has row numbers. Just remember S's and P's are the same as the row number, and D's are one less than the row number there.
Are F's?
And then you'll have the whole thing.
Only two
Are
are
F's
left.
two less?
Yeah, F's are two less. I don't expect, though, on the AP exam, they're going to ask you anything that's in the F's. Now, that probably means that they will, because I don't expect them to.
Wait, I got you.
I do expect them to only give you things like 50 and smaller. The 50's right here. Okay. I don't really think they're going to be hammering you with the biggies. I'm pretty confident about this. Okay, Whitney, I need you back.
S and P's are the same number on the periodic table row,
Yeah.
and then
D's
D's
are
one
one less than
and those
row.
are the transition nodes.
Yep. Yep. And F's would be two rows. So in the sixth row, there would be 6S, and then 4F, and then back up to 5D and 6P, all in the same row. Now we'll see that as we move along. And let's go ahead and move along. Like to this thing. And this is where I'm just talking through the order of things in the periodic table. Here's another way of representing the exact same thing. I'm sure you remember seeing this.
Yes. And then the arrows, you have to do all the up ones first.
I color-coded the energy levels. First energy level is in red. Second energy level is in green. Third energy level is where it starts to get interesting because first energy level has only one sub-level. Second energy level has two sub-levels. Third energy level has three. And as soon as you start working with D's, that's when we start to get the overlap into the next energy level. So there's 3S, 3P, and then 3D is up there after 4S.
Should we draw this again?
Yes, I think so.
Colors. How many colors is there?
Or we could just
Four?
follow
Four
the
colors.
chart left to right and just like.
Yeah, and this is the
Another
exact same
side.
order as when
Just
you go
like-
through the
Yeah.
periodic table.